Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Discovering Matter. This is a lab manual in Unit 1. Intro section, The Science of Cooking. Why does food change when cooked? Cooking is all about changing food. Think about the kinds of food that are found in a kitchen. Many kitchens have raw foods that haven't been cooked. Fruits and vegetables are raw foods until they've been cooked in some way. So is uncooked meat. And kitchens usually have foods that have already been cooked. Bread has already been cooked. Some food cannot be eaten until it has been cooked. Raw meat is an example of this. So are pasta and rice. The relationship between cooking and science. The changes that food undergoes in the kitchen are all caused by scientific phenomena. Cooking is chemistry and physics, except you get to eat your lab work, says Jack Bishop, who worked at America's Test Kitchen. It's important not to eat anything in your science lab because those materials are not edible. Broadly, science is the search for explanations about the natural world, and scientists use evidence to form conclusions that support those explanations. All knowledge learned from experiments is part of science. Using a scientific process. Science is part of a larger cycle that includes engineering, math, and technology. This cycle is called the STEM cycle. Engineers apply scientific knowledge to create new technologies that solve problems. Math is a tool that both scientists and engineers use to capture results and communicate those results to others. Scientists use a scientific process to guide them in developing a replicable experiment as they seek out answers to questions about the world around them. A process is a series of steps designed to meet a goal. There are 8 steps that scientists often follow to answer questions using data from experiments. These steps give scientists a logical pathway to move from a question toward an evidence-based conclusion. Step 1. Ask a question. Asking questions is something that all scientists do. Scientists look for the causes of different phenomena they observe in the world around them. The scientific process always begins with a question. For example, imagine that a scientist named Anna observed that her garden plant looked shriveled after a week of no rain. Scientist Anna might then ask the question, how does the amount of water a plant receives affect how tall it grows? Step 2, research the question. Every year, the amount of scientific knowledge grows. Scientists use this existing knowledge to research their question. Scientist Anna might research what plants need to survive and grow. She might learn that plants use water to carry out different life functions. Step 3, form a hypothesis. After scientists have researched their question, they form a hypothesis. A hypothesis is a statement that can be proved true or false. The hypothesis is the scientist's prediction based on what is known about the answer to the question. Scientist Anna might come up with one of the following hypotheses. Plants grow taller when they don't receive any water compared to when they receive water. Plants grow less tall when they don't receive any water compared to when they receive water. The amount of water a plant receives has no effect on its height. Step 4, write a summary of the experiment. Scientists then write a summary of the experiment they will conduct to test their hypothesis. The summary should include the basics of the data to be collected, the variables that will be tested, and the parts of the experiment that will remain constant in each test or trial. A variable is something you change. It can be a factor, trait, or condition that can exist in different amounts or types. There are independent and dependent variables in an experiment. The independent variable is what the scientist changes. The dependent variable is what happens as a result of the independent variable. In an experiment testing whether the amount of water a plant receives affects its height, the independent variable would be the different amounts of water the plant receives. The height the different plants grow would be the dependent variable. Constants allow scientists to isolate one variable at a time to ensure the experiment results are valid. For example, the type of plant used and the amount of sunlight would need to stay the same in each test. If the type of plant or the amount of sunlight were different, it would be impossible to know whether the results were because of the amount of water or the other factors. Step 5. List materials and procedure. Scientists then list materials needed and the procedure they have created that they will follow. A procedure is like a recipe. Whenever you use a recipe, you are following a careful and precise procedure that someone else developed. Scientists write down their materials and procedure so anyone can use the same materials and follow the same steps to get similar results. They also want to create a record of their thinking. Step 6. Draw a scientific diagram. They will also draw a scientific diagram. The diagram helps the scientists visualize how the different materials will interact in the experiment. Step 7. Carry out experiment to collect data. Scientists then conduct an experiment to test their hypothesis. An experiment is a scientific procedure that tests if a hypothesis is true, false, or inconclusive. Scientists use experiments to look for patterns in data that suggest a cause and effect relationship, where one event or thing is the result of the other. A pattern is something that happens in a regular and repeated way. The results of the experiment are data. Data are the measurements and observations gathered from an experiment. Step 8. Form a conclusion. After data have been collected, scientists form a conclusion. The conclusion uses data from the experiment as evidence to support whether the hypothesis is true, false, or inconclusive. The scientific process. Question. End with a question mark and do not include words such as I or because. Research. Include a minimum of 3 facts relevant to the question. Hypothesis. Write a concise statement that answers the question and can be proved true or false. Summarize experiment. Describe in 2 to 3 sentences the experiment you will do to test your hypothesis. Identify the independent and dependent variables, constants, and controls of the experiment. The independent variable is the variable changed. The dependent variable is what happens as a result of the independent variable. Constants of the experiment are conditions unchanged during each trial. A control in the experiment captures the effect of unknown variables. Materials and procedures. Vertically list all materials needed for your experiment with quantities. Next, vertically list the numbered steps of your procedure. Note safety precautions. Scientific diagram. Draw a diagram of the experiment setup that is at least the size of your hand. Title it and include labels for all materials on the materials list. Data. Follow your test procedure and gather data, both observations and numbers, to determine whether the hypothesis is true, false, or inconclusive. Use proper units, title data tables, and tape into lab notebook. Conclusion. Use the data collected in the experiment to explain why the hypothesis is true, false, or inconclusive. Every conclusion must contain a minimum of 3 elements. 1. Restate your hypothesis. 2. Make a claim, true, false, or inconclusive. 3. Use key points of data as evidence to support and explain your claim. Section 1. Using energy to change food. Food is matter. Today, Mario Batali is a famous chef, but he remembers watching his Italian grandmother making her own pasta every Sunday. She would put her homemade ravioli or gnocchi into boiling water to cook it. He says that watching her do this played a major role in his becoming a chef. Pasta is a kind of matter. Matter is anything that has mass and takes up space. Mass is a measure of the amount of water that makes up an object or substance. It is measured in grams. Properties of matter. The mass of an object is one property of that object. A property is an observable or measurable characteristic of a substance. Physical properties include color, texture, mass, volume, and density. Volume is a measure of how much space an object or substance takes up. It is measured in cubic meters for solids with a ruler, or liters or milliliters for liquid. Density is the amount of mass in a unit volume of a substance. Different elements have different densities. Density is a useful physical property for identifying an unknown substance because the amount or sample size of a material does not affect its density. Because most substances change volume when they are heated or cooled, densities are temperature dependent. Each kind of matter has the properties it does because of the atoms that make it up. An atom is the smallest piece of matter that has the properties of an element. An element is a substance made up entirely of one kind of atom. All matter is made up of a specific combination of atoms. To understand why matter has the properties it does, scientists begin with the structure of atoms that make it up. Structure is the way in which parts are put together to form a whole. Atoms are so tiny that we cannot see them without special instruments. Because of this, scientists use scale to understand how the size of atoms relates to everyday objects. Scale is the size, extent, or importance, magnitude, of something relative to something else. Scale of an atom. For example, think about a grapefruit. If each atom in the grapefruit were the size of a blueberry, the grapefruit would have to be the size of Earth. There are so many atoms in just one grapefruit that they are impossible to count. Imagine having to fill up the entire planet with blueberries. That's about how many atoms are in one grapefruit. Atoms themselves are made up of smaller particles called protons, neutrons, and electrons. These smaller particles are called subatomic particles. These smaller particles are much smaller than the atom itself. The protons and neutrons group together in the atom's core, called the nucleus. If the atom were the size of a blueberry and you opened the blueberry up, the nucleus would be too small to see. If you were to make the blueberry the size of a football field, you would just be able to see the nucleus. It would be the size of a small marble. The nucleus holds all of the atom's protons and neutrons. The electrons are smaller than the protons or neutrons. They are in constant motion around the nucleus. However, most of the atom is filled with empty space. There are vast regions of space between each of the electrons and between the electrons and the nucleus. How matter forms. Atoms are like Lego blocks, fitting together with other atoms to form bigger pieces of matter. Whenever two or more atoms bond, join together, they form molecules. Each kind of matter has the properties it does because of the number and kind of atoms and molecules that make it up. Molecules can be small, made up of one or two atoms, or they can be made up of thousands of atoms. For example, oxygen is a molecule made up of two oxygen atoms bonded together. It is a gas at room temperature. It is colorless and odorless. Hydrogen is a molecule made up of two hydrogen atoms bonded together. Like oxygen, it is also a gas at room temperature. It is also colorless and odorless. It has the lowest density of all the elements. Water is a molecule that forms when two hydrogen atoms and one oxygen atom bond. It is a liquid at room temperature. It is odorless and almost colorless, except for a hint of blue. The relationship between matter and energy. Matter cannot change without energy. This is why you need a pot of boiling water to cook pasta. Energy is the ability to do work. Work is any change in position, speed, or state of matter due to force, a push or pull that acts on an object, changing its speed, direction, or shape. Examples of work include heating an object or moving an object. Energy can either be stored or in motion. Energy that is stored is called potential energy. The energy of motion is called kinetic energy. Forms of energy. Energy is never created or destroyed, but it can change from one form to another. For example, all matter has a form of chemical potential energy that is stored in the bonds holding together atoms and molecules. That chemical energy is what allows new molecules to form. We'll explore this idea more in the next section. Chemical energy can also be transferred. For example, when we eat pasta and other food, we absorb some of the food's chemical energy. All matter also has a form of energy called thermal energy. Thermal energy is the motion of atoms and molecules in a substance or object as its temperature increases. Temperature is a measure of heat and is measured in Celsius with a thermometer. Heat is not the same as thermal energy. Heat refers to the thermal energy transferred from one object to another. The faster that atoms and molecules move, the more thermal energy they have and the warmer they become. Thermal energy changes matter's state. The amount of thermal energy present in a substance determines a substance's state of matter, whether a substance is a solid, liquid, or gas. Solids. Solids have the least amount of thermal energy of any state. As a result, the atoms in a solid are closely packed together. They are always moving, but because of how close they are, they can only vibrate in place. They cannot move past one another. As a result, solids keep their shape until something changes them. When thermal energy is added to solids, the atoms or molecules begin to move more quickly. When enough energy is added, they will expand and become a liquid. This is what happens when you leave ice cream out on a hot day. The ice cream absorbs thermal energy from the environment, causing the ice cream to melt. The temperature at which a substance changes from a solid to a liquid is called its melting point. Different substances have different melting points depending on how much energy is needed to change them from a solid to a liquid. This, in turn, depends on the kind of atoms that make them up. Liquids and gases. Water and milk are both examples of liquids. The atoms in a liquid are less tightly packed than in a solid. They are in constant contact with one another, but they have had enough energy to slide past one another. Therefore, matter in a liquid state takes the shape of its container, but has no shape of its own. When thermal energy is removed from a liquid, the kinetic energy of the atoms and molecules decreases. This causes them to slow down. When enough thermal energy is removed, the liquid will turn into a solid. This is called its freezing point. For example, water freezes when the temperature reaches 0 degrees Celsius or 32 degrees Fahrenheit. When enough thermal energy is added to a liquid, the atoms or molecules will move so quickly that the liquid will expand, becoming a gas. This is called a substance's boiling point. Water boils at 100 degrees Celsius or 212 degrees Fahrenheit. The molecules in a gas have so much energy that they move far apart and bounce around randomly. As a result, matter in a gas state has no shape and spreads out into space. If a certain amount of gas is taken out of one container and placed into a container that is twice as large, the gas will expand to fill the larger container. Energy transfer. Cold water in a pot eventually heats up and starts to boil when enough thermal energy is added. This happens because energy can transfer into or out of systems or objects. A system is a set of connected, interacting parts that form a more complex whole. If pasta is cooked on the stove, the pot and the water and pasta in the pot form a system. Heat transfers into the system when the pot is on the stove and the stove is turned on. Heat is energy that is transferred whenever two substances are at different temperatures. Heat always flows from faster moving atoms, a higher temperature, to slower moving atoms, a cooler temperature, until both substances reach the same temperature. This point is called equilibrium. Conduction. Conduction is heat transfer that occurs when molecules collide. When the stove is turned on, it heats up the surface of the pot. The warmer molecules of the pot collide with the cooler water molecules. This causes energy to transfer from the pot molecules to the water molecules. Section 2. Chemical reactions. Baking bread. Have you ever watched someone bake bread? The baker takes a variety of different ingredients. They follow a recipe to combine the ingredients in a specific way. Then they add heat to the mixed ingredients. After some time, a loaf of bread is created. When you bake a loaf of bread, chemical reactions occur. In a chemical reaction, the atoms of the original substances are rearranged into one or more new substances that have different properties from the original substance. chemical versus physical changes. The changes that occur as a result of a chemical reaction are not the same as physical changes. Physical changes are changes that do not affect the chemical structure of a substance. For example, if you cut up a piece of paper, it is smaller, but it is still paper. When you add enough thermal energy to an ice cube, it will turn into liquid water, but the molecules are still water molecules. The ingredients of salad dressing can be separated, and they will still have the same properties. In contrast, a chemical change is a change that rearranges the chemical structure of the substances through a chemical reaction. When you bake bread, the ingredients are combined in such a way that the bread is produced has different properties from the ingredients it came from. When you cook pasta, the noodles are chemically changed to become sticky and springy. When you cook, it is good to know about the properties of the different ingredients. These properties are determined by the number and kind of atoms that make up the different ingredients. But scientists often don't work with individual atoms because they are so small. Instead, they work with elements, substances made up entirely of one kind of atom. For example, salt is a staple of kitchens. It is made up of the elements sodium and a form of chloride, so it is called sodium chloride. Periodic table of elements. Scientists use a chart called the periodic table of elements to organize all of the atoms' known elements according to their properties. There are currently 118 known elements. The last 4 were just added in 2016. Scientists are continuing to search for new elements. Each element on the periodic table is assigned a symbol and a number. The symbol comes from the name of the element's atom, in English or Latin, and the atomic number comes from the number of protons found in the atom's nucleus. For example, sodium has 11 protons, while chlorine has 17. Neutrons and electrons don't define an element because the number of neutrons and electrons in an atom can fluctuate. Organization of the periodic table. The periodic table is organized from top to bottom in groups by increasing atomic number. The periodic table indicates some patterns among elements. For example, an element's place on the periodic table tells us how reactive its atoms are and whether it is a metal, nonmetal, or metalloid. Metals are shiny, malleable, and good conductors of electricity and heat. Almost 75% of all elements are metals, including mercury, zinc, gold, copper, iron, and other elements in columns 1 through 12 of the periodic table. Nonmetals are brittle, dull, and poor conductors of electricity and heat. There are only 18 nonmetals on the periodic table. Gases and elements on the far right of the periodic table are nonmetals. Coal is an example of a nonmetal. Metalloids, also called semiconductors, have properties of both metals and nonmetals, such as being shiny and hard but brittle. Boron, silicon, and arsenic are metalloids. Metalloids are found between metals and nonmetals on the periodic table. They are called semiconductors because, depending on what other molecules are around, they can sometimes conduct electricity. So here is the periodic table. Whenever 2 or more atoms bond together to form molecules, or when bonded atoms are broken apart, a chemical reaction occurs. A result of this process is that the substances formed has different properties than the original substances. For example, at normal room temperature, both oxygen and hydrogen elements are gases. When hydrogen and oxygen bond in a molecule of water, they change into a liquid instead of a gas at room temperature. In any chemical reaction, the atoms and molecules that interact together are called reactants. The atoms and molecules produced by the reaction are called products. Together, the reactants and products form a system. The environment is everything else, including the air or any substance mixed with the reactants. Conservation of mass. The total number of atoms does not change in a chemical reaction. Because of this, the mass of any one element at the beginning of a reaction will equal the mass of that element at the end of the reaction. This is called the conservation of mass because matter is never created or destroyed. This means that the more reactants you add to the chemical reaction, the more products will form. It is always true that mass is conserved in a chemical reaction. However, this can be difficult to measure in the real world because the chemical reaction system can interact with the environment. Remember that if a gas is produced, it will fill whatever space it is in. This is impossible to measure. For this reason, scientists sometimes conduct closed system experiments. These experiments are designed so that matter cannot be exchanged with the environment. This allows scientists to measure the effects of the reaction. Energy in a chemical reaction. As the reactants combine and rearrange, energy is exchanged between the system and the environment. It's important to note here that reactants are sometimes dissolved in other substances such as water. The dissolving substance, such as the water, is called the solvent. When this occurs, the solvent in which the reactants are dissolved is part of the environment. Every chemical reaction needs energy to get started. This initial input of energy is called activation energy. For example, when someone strikes a match to light a candle, they provide the activation energy needed to start a fire, which is a chemical reaction. Once the reaction begins, some reactions absorb more energy from the environment than they release. Others release more energy into the environment than they absorb. Endothermic process. Whenever a process occurs in which the system absorbs heat, it is called endothermic. Endo means to draw in. In an endothermic reaction, the environment's temperature decreases. This is because the reaction has absorbed energy from the environment. Exothermic processes. Any process in which the system loses heat to the environment is called exothermic. Exo means to give off. Because the energy is released as heat, the environment's temperature will increase. There are many examples of exothermic chemical reactions. When you light a match, an exothermic reaction takes place. The light and heat produced are evidence that energy is being released into the environment. Another common example of exothermic reactions occurs in certain animals that produce and release light, called bioluminescence. This phenomenon occurs in animals that live in the ocean, as well as some land animals such as fireflies. The strength of a chemical reaction can be measured by the amount of energy absorbed or released by the reaction. When more reactants are added, it increases the amount of energy that is absorbed or released. In the know, endothermic versus exothermic. The difference between the different kinds of reactions can be understood by thinking about the amount of energy held in the products compared to the amount of energy held in the reactants. Endothermic reactions. In an endothermic reaction, the reactants have less energy than the products. Because energy is never created or destroyed, the energy needed to form the products is absorbed from the environment into the system. We can't observe these changes at the molecular level, but we can measure the temperature change that results. We see evidence of this transfer of energy when the environment's temperature decreases because it means that the reaction has absorbed energy from the environment. Exothermic reactions. In an exothermic reaction, the reactants have more energy than the products. Because energy is never created or destroyed, energy is released by the reactants and transferred into the environment as heat. Section 3, Design Challenge, Ice Packs. Preserving food. No food will last forever. In time, all foods decay. When this happens, we can no longer eat them. Before people had refrigerators and freezers, they used blocks of ice in a container to keep foods cold. The cold slowed down decay. When refrigerators and freezers were invented, they helped solve the problem of food spoiling by keeping foods fresh for longer periods of time. However, it was still difficult to keep foods cold for extended periods of time when you didn't have access to a refrigerator. Engineering solutions. In the 1950s, engineers began using what they know about heat transfer and chemical reactions to design instant cold packs. Engineering is different from science, although science and engineering are connected. Remember the STEM cycle. Scientists use experiments to gain knowledge. Engineers use that scientific knowledge and mathematics to create new technologies that solve problems. A technology is anything that people have modified from the natural world to meet their needs and wants. Similar to how scientists follow a scientific process to answer a question, engineers also follow a process. Engineers often follow a process with 8 steps that guides them as they create new technologies to solve problems. The engineering process is similar to the scientific process, but it differs because each has a different goal. Scientists are trying to answer a question, while an engineer is trying to solve a problem. Step 1. Identify a problem. The engineering process begins with a problem. When engineers are defining a problem, they include the criteria, the needs the solution must meet, and constraints, ways the solution is limited. Available materials and cost are 2 common engineering constraints. For example, the first instant cold pack was designed to solve the problem of keeping food and drinks temporarily cold when ice wasn't available. Step 2. Research the problem. Once they have identified the problem, engineers need to research it to find out what is known about the problem. For example, engineers designing an instant cold pack would need to know the following scientific information. Thermal energy can transfer into or out of objects or systems. Certain substances can combine in an endothermic chemical reaction. Because thermal energy absorbs, the environment becomes colder. Adding more reactants increases the amount of energy that is absorbed. Reducing the amount of reactants decreases the amount of energy that is absorbed. Step 3. Survey available materials. After engineers have researched their problem, they survey the available materials. This survey includes a sketch of the material, as well as how much of the material they have available and the properties of that material. Step 4. Come up with possible solutions. Engineers then come up with possible solutions for how the problem can be solved with the available materials. For example, one possible solution is to combine 2 substances, such as water and ammonium nitrate, that will combine in an endothermic reaction. The 2 substances will have to be separated by a barrier that can be broken, so the 2 substances can combine and react when the pack needs to become cold. Step 5. Diagram and build a prototype of the solution. Once engineers come up with a possible solution, they diagram and build a prototype. A prototype is a scaled-down first draft of a technology. Step 6. Test the prototype. Once built, engineers test the prototype. They want to see how well it works and whether it meets the criteria of the problem within the constraints. Step 7. Collect data. They use the tests to gather data about how well the prototype solves the problem during testing. Step 8. Refine or replicate. Finally, engineers use their data to decide whether to refine or replicate. If the prototype doesn't work in some way, engineers know they need to refine their design. They need to look at what didn't work and come up with ways to improve it. If the prototype solved the problem, meeting the criteria within the constraints, the engineers will replicate their design. This means they will use their design and scale it up to create a full-sized version of their technology. Designing new materials. New technologies can then be used to solve other problems or help scientists investigate further scientific questions, continuing the STEM cycle. For example, instant cold packs have evolved so that they can be used on people to reduce swelling and ease muscle pains. This is useful in situations when natural ice is not available or not practical. The kind of material to wrap the reacting substances is one challenge for the instant cold pack. It has to be flexible enough to fit the natural curves of the human body. It also has to be insulated so that it doesn't become so cold that it burns the person using it. Synthetic materials. Engineers have designed various synthetic materials. A synthetic substance is one that is formed through a chemical process developed by humans as opposed to those of natural origin. Remember that all matter, both naturally occurring and synthetic, is formed from combinations of the 118 known elements. Synthetic materials are created from those naturally occurring elements that combine in chemical reactions to produce new and different kinds of matter. In order to make synthetic materials, engineers need to know about the properties of different substances and how those properties will change in chemical reactions between different substances. They use that scientific knowledge to evaluate how well the proposed synthetic materials will meet the needs of the problem at hand. Using an engineering process. Problem. Identify the problem, including the criteria and constraints of the problem, and summarize in 2 or 3 sentences. Research. Use what you know to help solve the problem. Record a minimum of 3 facts relevant to the problem. Survey available materials. List the available materials that could be used to solve the problem, and include for each material a sketch, quantity, description, and properties. Possible solutions. List 3 ways the problem can be solved with the available materials. Diagram and build prototype. Draw a hand-sized scientific diagram of the prototype solution you will then build from your materials. A scaled-down version of a technology is called a prototype. Title the diagram and include labels for each material are part of your prototype. Test. Test your prototype to see how well it solves the problem. Data. Collect data, measurements, and observation as evidence for how well the prototype solves the problem. Refine or replicate. Use your data to evaluate the success of the prototype and recommend if it should be refined or replicated. You may redesign your prototype to better solve the problem. Every conclusion must contain a minimum of 3 elements. 1. Restate the problem and describe the prototype technology. 2. Make a claim about whether the technology should be refined or replicated. 3. Use key points of data gathered from testing to support the recommendation to refine or replicate. Wow, I really learned a lot reading Discovering Matter. I hope that you did too. I'll see you tomorrow with another one. Bye.